Hi, my name is Blake Johnson. I'm the quantum platform lead at IBM Quantum. I lead the technical team that builds our control stack at IBM and organize many of our efforts on the software stack that used to program and manipulate quantum computers. I'm excited today to tell you about some of the future directions of quantum software in the cloud. Back in 2016, we at IBM launched the quantum experience and put the first quantum computer online. We were very excited that that first week we had over 6,000 users use our system through the quantum experience. And now, 4 years later, 4.5 years later, we've had over 200,000 people submit a circuit to an IBM quantum system. But there's many more developers in the world, over 20 million, and we want to make our systems accessible and usable by all of them. And so that's has us asking the question of will it take to go from here to there? What will it take to make these systems usable and meaningful to the broad community of developers that are out there in the world? And one of the things that we realize that's going to be required is that the hardware needs to get better. This is why we announced our hardware roadmap earlier this fall to build a successive series of systems with increasing scale and performance. Going from the Falcon and Hummingbird based systems that we've been deploying this year towards in 2023 a 1,000-qubit platform known as Condor, and then the components and the path towards even much larger systems thereafter. This Condor-based system, is not just about scale. However, it is also about performance, and we're continuing to drive down error rates in these systems to greater and greater quantum volumes. And part of the idea here is the intent is that this Condor system is really an ideal platform for experimenting with ideas of quantum error correction. But in order for that to really be possible, not only do we need a large quantity of qubits with low error rates, but there's a critical missing piece that the system also must have for us to really, for this to be a fertile playground for quantum error correction, and that is real-time classical compute. So that is something that we also need to add to our systems. If you actually look at the kind of workloads that we try to execute on quantum hardware, you'll notice that we often put our attention on the quantum part, the circuit, what has traditionally been called a circuit. But the actual workloads, the actual jobs that have to run really correspond to an interplay, an interaction between quantum and classical resources. And this is true both for near-term use cases like variational quantum algorithms, but it's certainly true also for the fault-tolerant regime and for error correction, where I also need this kind of interaction. And so we've noticed, we've been looking at cycles like this and trying to design our systems to better be able to handle them. One of the things we've noticed is that actually this loop is not as simple as is shown here. It actually there's multiple levels of hierarchy. There's a hierarchy of latency scales that matter in interactions between quantum and classical workloads. As we've begun looking into how to build systems which can efficiently execute workloads that have these interactions between quantum and classical resources, we've noticed that there's actually several discrete domains of latency. There's a real-time domain where we need the classical resource the classical computing to interact with the quantum system within the coherence times of the qubits. And this is a very demanding domain where perhaps the classical resources are somewhat restricted, maybe they're in terms of space or time and so on. But we need very tight loops. And there's also a more generic domain in terms of which maybe only requires near-time interactions. We still want them to be fast, but we're really demanding kind of access to general-purpose classical computing. And so to tackle these two different domains, we're actually approaching them separately with a new programming interface that describes together the real-time and quantum domains, which we're calling OpenQASM 3. And then for that near-time domain, we're building a Qiskit runtime, which I'll tell you about a little bit later, that can handle these generic classical computations. So let's look first at the real-time domain. So as I said, we've proposed a new extension to the OpenQASM language that we're calling OpenQASM 3, which together describes a new circuit family which contains together what the quantum operations together with real-time classical computation. So, enabling these kind of workloads requires both the new software interfaces as well as the compiler and hardware systems to execute them. And we're really working on both the software and hardware components. Starting with, we have a proposed specification for an extension to OpenQASM that we're calling OpenQASM 3. So this is now up on GitHub. You can go look and comment and give us feedback. But I have a little example to show you here on the right-hand side of what an iterative phase estimation program would look like written in our proposed syntax for OpenQASM 3. And a couple of the new things that are going on here is that you have classical data types like a fixed point angle type or an unsigned integer type. You have manipulations of those classical values at runtime, like with shift operators, addition, regular arithmetic. And crucially for this particular example, the actual the quantum operations can depend on that classical data at runtime, like this phase operation which acts on this classical value C, which is being updated by the execution of the circuit. And so, like I said, the OpenQASM 3 syntax and language is really just a start, and we'll be continuing to work on the entire system stack necessary to execute this. Actually, as a first example where real-time compute can be beneficial is in the use of initializing a quantum register into its initial state, something we call conditional reset. And we've actually just over the course of the last few months been deploying conditional reset as an initial use case for real-time compute across our fleet of quantum systems. But what we're doing with OpenQASM 3 and all the software and hardware to support it will be a dramatic extension of this domain of real-time compute. The other thing that we need, though, is this near-time domain. And so we realized that for a high-performance system, we also need to build the low-latency reaction to generic classical compute. And you can see the importance of this domain by looking at real workloads. So take an example in chemistry where I want to solve, in this particular case is taken from a paper a few years ago where we looked at calculating the binding energy of a lithium hydride molecule. And this particular experiment required about 5 billion circuits to execute, including the error mitigation that was applied to extract better accuracy from today's hardware. If you were to run the same exact experiment, you didn't make any programming mistakes, you got it exactly right the first time, it would take you over 100 days on our current system. And this runtime is largely dominated by the quantum classical execution model that's available to you today. However, we believe that if we can integrate our execution system into a hybrid cloud fabric, that the same calculation can be done in about 16 hours. So there's a dramatic benefit that's out there by integrating classical and quantum computations. And so to see why this is slow, in today's execution model, when you're doing one of these near-term algorithms that has a variational structure, you might have a classical optimization loop that's producing circuits and producing using data from the execution of those circuits in order to update some prior and produce new circuits. And so you have, on the user's machine, on their laptop or whatever, a classical optimization loop that's interacting with quantum hardware via a queue. And so you look at this model, you can understand that it, of course, is going to be slow because inside the sort of the inner loop of your algorithm, you have this queuing mechanism, which is critical to be able to share scarce quantum resources. So we want to transition from this model today to a model which looks more like this one in the future, where instead of submitting circuits to a queue, I instead could submit a program. And that program would be executed in a new runtime that would be on the other side of the queue. And the generation of circuits interacting with hardware would happen sort of in this execution layer on the other side of the queue. So your tight inner loop can now be over here rather than having to go all the way back to the user's machine. So this model can dramatically accelerate workloads. We've actually are in the process of building prototypes of this system. And I have a demo to show you today of one such prototype, where on the left, this is a prototype running against a simulator. On the left, you're seeing that the current execution model, where the user is submitting jobs to a cloud-based simulator, where each one of these, each circuit or circuit batch needs to be a sort of independent job. And on the right, you see the new model where the user uploads a program and then remotely invokes execution of that program. And then the last thing this user is going to do is basically listen in as that program is executing to sort of check in on it and see how it's going. And what you'll notice is that even in this simulation environment, this new Qiskit runtime model allows for a significant speed up compared to the model that's available today. What we're seeing in our initial prototype is something which takes 6 minutes of simulation down to just 12 seconds. So we are actually quite confident that we can find similar speed ups, similar performance improvements when running against real hardware. Another amazing benefit of this model is that when the interface is at the program level rather than the circuit level, that really makes it much more straightforward to build higher level interactions. And just to kind of prove the point, we put together another little prototype that I have to show you today of interacting with a quantum system from something which doesn't feel like programming at all, which is just a spreadsheet. So in this particular prototype, the user effectively is describing the geometry of a molecule they want to simulate, and then just asking for that runtime to effectively execute their simulation from just this simple geometrical description. And again, the point of this isn't that interacting with quantum systems from a spreadsheet is the way that users are everywhere going to want to interact with quantum systems, but just that if you can do it here, that really means that you really can do it from anywhere. And so this is part of our dream towards making quantum systems easier to use, make the experience in some ways frictionless. And if you kind of step back a minute for what we're going after, we're trying to change the interaction model of quantum systems from always being at the circuit level to sometimes to higher degrees of abstraction. From allowing our users to, instead of always having to think about sort of gates and wires in a circuit, to allow them to basically pop up to a higher level of abstraction. And so when we're thinking about how to build a frictionless experience, we have the kind of the right kind of experience we have to build depends on the kind of developer that you are. And so our efforts today focus on several different kinds of developers, from kernel developers that are building the lowest level components. These are maybe circuit components or even gates that they want to optimize. To algorithm developers, I want to take those components that the kernel developer has built and put them together into algorithms that can do useful work. And finally, the model developers that are going to take those algorithms and apply them to particular problem domains to connect them to real-world problems. So again, our efforts span many different kinds of developers. And so let's put our attention first on the algorithm and kernel developers. whose work is still largely about creating circuits. But if that's what they want to do, then we better make it easy to create circuits. And so our Qiskit programming framework has a powerful toolbox in order to construct circuits more easily, more efficiently. For the kernel developers, we have things like a pulse builder syntax for describing really the signals that you want to send down the wires that are connected to the system, or ways to construct circuits at the gate level, but with timing, with simple alignment primitives. For the model developer, we have different kinds of tools, like the ability to describe circuits in terms of kind of algebraic concepts or mathematical concepts like unitaries or Clifford operations. We also have a library of sort of pre-built circuit components, like the quantum Fourier transform that you can use without having to specify exactly how the Fourier transform is built. This is actually maybe the concept which is most familiar from classical programming, where a lot of the developer experience has to do with importing and using libraries of existing components to do their work. In this particular case, the most relevant analog is like math libraries, which are used kind of universally in numerical programming. Just to say a few more words about the circuit library, we actually have two different kind of families of circuits, from kind of immutable circuits that are described, that describe things like adders, Fourier transforms, and so on, and in some ways have a recursive structure, like this Draper adder here, in fact, contains like the quantum Fourier transform inside it as a subcomponent. But we also have circuit patterns, which are not complete circuits of themselves, but maybe analogous to also design patterns in classical programming. They're things that appear over and over again that when you kind of fill in a component in a template, you end up with a circuit. And so an example of a pattern in the Qiskit circuit library today is this excitation preserving pattern, which you see as applications to various variational ansatz where you want to preserve where you have an encoding that represents like occupation of a state or an orbital, and you want from the symmetry of the problem that you need to have the same number of the same occupation number at the end of the circuit as you have at the beginning. For popping up to the model developer layer, again, these are subject matter experts that want to apply quantum computing to the field, but maybe they're not experts in quantum computing itself. And so we're trying to provide an on-ramp to engage this community, to get them interested in and up and running with quantum programming. And for these model developers, the approach that we're taking is to allow them to use quantum systems at the problem specification layer rather than at the circuit layer. Right? We want these model developers to be able to describe the problem that they want to solve, and then we'll try to take care of as much of the details as possible of converting that problem description into a circuit or a family of circuits that can solve their problem. So in the first example of a library of a module that we've produced for these model developers is the Qiskit optimization module. So in this this framework, you can basically describe an optimization problem in terms of variables and constraints. You pick a solution method, and then you can solve. And I want you to notice this is a real code snippet. Nowhere in this snippet does it mention qubits. Right? The circuits are kind of hidden, but we've also built it in a modular way so that this is a great way to sort of get started. But then once you sort of discover what works and what doesn't, you can start to kind of peel apart what's going on and start to modify it and hopefully make it work. And then, again, this is all toward this dream of taking this miraculous, marvelous technology and trying to make it invisible, right? To have it just work for real problems. And we believe that if we're successful in doing this, then really this large community of developers will really find value in quantum computing. You know, it will have impact in the way they work. So thank you for your time. And it was my pleasure to be able to tell you a bit about where we're going at IBM Quantum.